Chapter 8, Sampling Distribution and Estimation. In this chapter, we talk about the sampling variations, estimators and sampling distributions, sample mean and central limit theorem, confidence interval for mean with known sigma, confidence interval for mean with unknown sigma, and confidence interval for proportion. And sample size determination for mean, and sample size determination for proportion. Those are optional for you just to study, and we're not going to cover them in the test. Okay. Let's talk about the sampling variation. First, what is sample statistic? Sample statistic is a random variable whose value a random variable whose value depends on which population items happen to be included in the random sample. Because when you take a random sample, you know which item in the population will be picked, will be included. So that itself, that's a sampling statistics, right? So depending on the sample size, the sample statistic could either represent the population very well or differ greatly from the population. Of course, that's not good, right? So this sampling variation can be illustrated in the following example. For example, like GMAT score. For those of you who will be taking a GMAT score, GMAT test, and apply for MBA program or graduate school in business, you will do that. Right? And let's consider 8 random samples of size n equals 5. I take 5 students from large population of GMAT takers, their scores for the MBA applications. Okay. You take 5 from the population. The population, let's say, for example, sample 1, you take 5 people's score. The 5 people's scores are 490, 580, 440, 580, and 430. And the average of the 5 is 504. By the way, the sample mean is calculated, but the population mean for all the people taking GMAT scores for the MBA applications in that year is 520.78. So the mu, or the mean of the population, is 520.78. Right? Now the sample 1 is 504. Right? That's for the first sample. Take 5 people, 5 students, 5 applicants. And if you take another 5 applicants in sample 2, there is a low score of 310, there is high score of 730, and the 590, 710, and 540. The average gives 576. If you take a third sample, okay, the average is 528. Sample 4, 500. Sample 5, 540. Sample 6, 496. Sample 7, 564. And sample 8, 582. So in other words, you can see that there's a variation. There's huge variation in the scores of the applicants, right? From as low as 310 to as high as 730. I believe that's the highest one, right? And there's huge variation from 300 to 700. And the mean is 520. But if you look at the means, the mean of samples, 504, 576, 528, 500, 540, 496, 564, and 582, all of them are kind of like quite close to the population mean. Now that's interesting and that's meaningful. Basically, you put them on the dot plots, you show it shows better. This is sample 1, the first 5 numbers here. Sample 2, sample 3, 4, 5, 6, 7, 8. The blue dots represent the actual scores, right? And the red dots here, the red line here, shows the average of the group. You can see that the sample means have much less variation than the individual sample items. Okay. Now, there's some terminologies about estimators and sampling distributions. An estimator is a statistic derived from a sample to infer the value of a population parameter. That's the estimator. We use something from a sample to tell about the population. And estimate here, estimate is the value of the estimator in a particular sample. And population parameters are represented by Greek letters and corresponding statistic by Roman letters. In this case here, population parameters, mu, sigma, pi. Mu is the mean, sigma standard deviation, pi is the proportion. And that's population parameters. We take a sample from that. In the sampling process, we move that to the sample. This is estimators, sample estimators. For the sample, we're going to have a mean. Instead of mu, we use x bar for samples. We use s for standard deviations. We use a little p for the proportions. And then we use the sample estimators to make an inference, to estimate, to guess, about the population. That's the whole concept. Okay? So example of estimators. For sample mean x bar, we use to estimate the population parameter mu. For sample proportion p, we use that to estimate population parameter of pi, also proportion. For sample standard deviation, then we estimate population standard deviation of sigma. Okay. Sampling distribution. Basically, the sampling distribution of an estimator is a probability distribution of all possible values the statistic may assume when a random sample of size n is taken. Right? When you take a sample of size n, and then what is the distribution? Right? It's a random sample, and that distribution, probability distribution, is a sampling distribution. An estimator is a random variable since the samples vary. Okay? Then the sampling error is the theta hat, or the estimated value minus the true value. That gives the sampling error. When you have different samples, you introduce a bias. Basically, the bias is the difference between the expected value of the estimator and the true parameter. And bias is defined as the expected value of theta, the parameter estimated value, minus true value. So the estimator, we call it unbiased if the expected value of theta is equals the true value of theta. Theta in this case refers to NA parameters. On average, an unbiased estimator neither overstates nor understates the true parameter. That's the ideal case. Okay. Efficiency. Efficiency refers to the variance of the estimator's sampling distribution. A more efficient estimator has a smaller variance. Yeah. In this case, a more efficient estimator is this red one, when n is to 880, and that's more precise, more efficient, is better than one like when n is 20 or n is 5. You can see that. Consistency in the estimating. A consistent estimator converges towards the parameter being estimated as sample increases, in the case of here, shown in this picture here. Right? There is a very important theorem in the statistic, that is the central limit theorem. Basically, it says, if a random sample of size n is drawn from a population with the mean sigma and the mean mu and the standard deviation of the sigma, the distribution of sample mean x approaches a normal distribution with mean of mu and standard deviation of sigma x equals sigma over the square root of n as sample size increases. Basically, what it says is, if you have a sample, when you increase the sample, the mean and the standard deviation of this sample, approaches a normal distribution. Now, this is very important. We studied normal distribution in chapter 7. Now, if this follows a sample distribution follows a normal distribution, we can use a normal curve, normal distribution table. Remember the z-score, standard normal, to make an estimation. So if the population is normal, the distribution of sample means normal, regardless of sample size. Now that's a great theorem. That's very useful. Okay. Basically, this is the concept here. This is normal distribution. You can see that. The normal distribution with mu and sigma. Mu is the mean, sigma is standard deviation. And if you take a sample from that, right, from the population, this is what we have. For the sample, the mean is still mu, still the population mu, mean, but the sample standard deviation is going to be sigma divided by the square root of n. So therefore, the standard deviation is smaller. The resulting chart shows a narrower, taller peak. It's a better estimator. Okay. As sample size increases, the distribution of sample means narrows on this population mean of mu. You can equal when you n increases from 1 to 2 to 4 to 8, you can see the peak gets higher and higher. So the sample means narrows on that. Okay. And also, if the sample is large enough, the sample means it will have approximately a normal distribution even if your population is not normal. Now this is even more interesting, more important. That is, if you have normal distribution, the sampling distribution is normal. But if you have a uniform population, the sampling distribution is going to be a normal. And this triangular population is still normal. Exponential sample distribution, sampling distribution is still normal. Now that's the amazing part of the central limit theorem. And this chart illustrates the central limit theorem. If we start out with a uniform population like here, right? You take the mean, this is the mean, when sample size of 1. With sample size of 2, you see it's more like a normal now. 4, very much like normal. 8, very, very much as normal. If it's a skewed population like this one, as you increase sample size, you can see the sampling distribution looks more closer to a normal distribution. Okay. So all possible samples from a uniform population. Let's consider this a uniform population, considering of integers 0, 1, 2, 3. Right. This is the population, only 4 numbers here. Right. And the population parameters are mu is 1.5. How do you get 1.5? Add this 4 together, divided by 4, you get 1.5. And you should know how to calculate the standard deviation also, right? That's 1.118. Okay? And then if you plot this, the sampling distribution, the each is 0.25 is a uniform distribution. The sampling distribution, sample means is, if you plot it, it's going to show something kind of like a peak, kind of similar to our normal distribution. Next, let's talk about the concept of a confidence interval for mean. So what is a confidence interval? Sometimes when we estimate, we cannot pinpoint as to give a true number, true value that represents the population mean. Instead, what we can is we can give not the point estimate, but the interval of estimate. A sample mean is a point estimate, but the confidence interval for the mean is a range that is also used. Right? Basically, for this confidence interval, we have an upper limit, we have a lower limit. Then what is confidence level then? The confidence level is the probability that the confidence interval contains a true population mean. Because instead of giving a point estimate, we give you a range. But within this range, what is the probability that the true population value, true population mean, is actually inside this range? And that's reflected in your confidence level. Or normally, conversely, we actually choose confidence level first, and then we'll give you an estimate. For example, when we say, let's take example here. Let's say what is the average age of USC Aiken students? We have 3,000 students. The age, let's say, I'm just making it up. Let's say the average age is 20 years old. Okay. Now, what is the confidence level? I can say that's the point estimate. But I can also say I'm 95% confident, or 95% of students will have an age between, say, 18 and 23. And that will be a confidence interval, right? At the confidence level, in this case, is 95%. Now, how do we calculate this? The confidence level, usually expressed as a percentage, is the area under the curve of the sampling distribution. The confidence interval for mu with a known sigma is this. It's given on this slide here. This is the mu, the point estimate, and x bar is the sample mean minus z-score. We talk about z-score right here, just below here, just a second. This is population standard deviation divided by square root of n. X bar minus that give you the lower limit. X bar plus that give you the upper limit. This is x bar minus that. This x bar plus that. This area is the confidence level. And the z-score, what z-score do we use? If you want to choose a confidence level of 90%, the z-score is 0.05. Since it's a 0.05, 5% on each side is 1.645. For 95% confidence level, use z-score 1.96. 98, 2.32. 99, 2.576. So depending on the level of confidence you want to have, we can use different z-scores to calculate confidence interval. Okay? And choosing a confidence level, a higher confidence level leads to a wider confidence interval. Do you believe that? Think about that. A higher confidence level leads to a wider confidence level interval. Sorry, let me do it again. A higher confidence level leads to a wider confidence interval. Why is that? Because you want to be more confident, right? You have to increase your range. You have to increase your confidence interval to make sure you contain a higher level, or let's say 90% or 99% of all the values. Okay? 95% confidence level is most often used, as you may know. Okay? Student T distribution. From this point on, from page 20 on, you will not be tested on this. We will not include that in the test. It's just for your knowledge, for your interest. If you're interested in this material, basically we use student T distribution instead of normal distribution when the population is normal, but standard deviation is unknown. The sample size is small. Then we use student T. Right? There's confidence interval for mu when the unknown sigma is t, with the t the student t level. Right? In student t distribution, it's symmetric and shaped like standard normal, almost same like standard normal, very much, and n is large, and it's from here to here. You can see it's very much like a normal distribution. Okay? And also there's a concept of degrees of freedom. That's a parameter on the based on the sample size that's used to determine the value of t statistics. So you know and as n increases, the t distribution approaches normal distribution, and the t values differ substantially from normal for very small samples. Okay? But as degree of freedom increases, the t value approaches normal z values. Okay? And this is the confidence interval for mean with unknown sigma for Gmax, same Gmax score. And if we do that, we will construct 90% confidence interval. The x bar is the average sample is 510, standard deviation 73.77. Since the sigma is unknown, we use student t for the confidence interval. The degree of freedom is 19. And we use a t table in the appendix D. You find the t score, then you can calculate the confidence interval. This is just so you know. We're not going to test you on that, right? And for beyond the mu of 50, the appendix D shows the V in steps of 5 or 10. Okay, and this is used to calculate the sample size to estimate mu. And just for your knowledge, you can actually just study it on your own, but we would, again, as I said, I'm not going to include that in your test. Okay, I think that's all for chapter 8.